All right, good morning. Today we're going to get ourselves started on section 3.5. And in this section, all we're doing is looking at applications. So nothing really new. It's just essentially combining some of the previous applications we've been talking about with the solving of the equations that we've been working on the last couple of days. So I couldn't remember the exact numbers. I'm just doing the best I can. We had a problem when we first introduced section 1. We had a birthday problem, and we pretended that somebody had a long lost aunt or uncle who gave them a $5,000 birthday check. And then we invested it in a mutual fund that was going to give us 12% return. Now, at the time, what we asked was, how much money would we have after a certain number of years? And for whatever reason, I think the number was like 25 years or something like that. And we were able to make the calculation fairly easy. Well, I'm just going to change up the question on everyone a little bit. And the question today is going to become, if you got the $5,000 birthday check as a 17-year-old, you guys would all be turning 17, I believe, or 18. And you could make 12% interest per year. For how many years would you have to have it in the account before it turns into $1 million? Okay. So that's the question. So our initial equation is going to be this one, and I'm going to choose to use the continuous compounding equation. It's a little bit easier to use. So the continuous exponential growth, or the continuous compounding equation, is a sub t equals a sub 0 times e to the RT power. Okay, and let me choose my little arrow tool here. Okay, so a sub t is the amount of money after time t. A sub 0 is the initial amount of money. E is our natural base. That's that 2.71828 number. R is the interest rate as a decimal. And t is time, the number of years. And of course, that's what we're going to be searching for in this case. How many years does it take for the 5,000 to become $1 million? So we're looking for time. Okay, so here we go. The amount of money we want this birthday check to turn into is $1 million. So we're going to replace a sub t with $1 million. The initial amount of money that you guys got for your birthday was $5,000. And the interest rate is 12%. Again, we always have to change that to a decimal. And I'm going to just use parentheses so nobody loses track of the decimal point. Okay? And so once we replace a sub t with $1 million, a sub 0 with 5,000, and r with 0.12, there's only one variable left, and it's the t. So we're just simply solving an equation like we've done the last couple of days, solving this for t. Okay? So here we go. To get rid of times 5,000, we'd have to divide both sides by 5,000. So 1 million divided by 5,000 is going to leave me with 200. All right. Next, the variable's in the exponent on the e. So to get it out of there, we have to do the inverse of an exponential. And the inverse of an exponential is a log. Which log are we going to use? Well, since it's base e on the right-hand side, we're going to use the ln. So we're going to take the ln of the left-hand side, and we're going to take the ln of the right-hand side. Okay? Now, on the right-hand side, since ln and e are inverses of each other, those two folks are just going to cancel each other out. I'm just going to scooch up to the side here so you guys can see this. So what we'd have is the ln of 200 is equal to then 0.12 times t. And to solve for t, we just have to divide both sides by 0.12. And so what we'll get as a result is the ln of 200 divided by 0.12, which makes no sense to us in terms of how many years is that. So we use our calculator to approximate that. So we'll take the ln of 200 and then divide by 0.12. And you'll see that if you were to leave it for approximately 44.2 years, the $5,000 birthday check would then turn into $1 million. And since, again, let's just say, again, I forgot who got the birthday check, but let's say it was a 17-year-old Excuse me. So after 44.2 years, then you'd be 61. Just a bit over 61, that $5,000 check would turn into $1 million. Not a bad return on the investment. Pretty good profit, so to speak, on that after so many years. Okay. Now, because this is a video, feel free to pause the video whenever you need to if you're putting any of these down in your notebook. All right, so feel free. Okay, I'm just going to keep buzzing along, but feel free to pause if you need to. All right, the next one is going to be an exponential growth problem. So we're actually going to use our same starting point. We're going to use a sub t equals a sub 0 times e to the RT. We're going to assume that these bacteria in this problem are going to grow exponentially. Now, we're going to use the version that has the e in it, because bacteria would, of course, grow continuously. They're not going to grow, by the hour or something. They're going to grow continuously. Okay? Now, as you read the problem, as you check it out, you can see 2 hours after the bacteria were introduced into a culture, the population was 256. 5 hours after the start, the population was 541. What will be the population 24 hours after the start of the experiment? So how many bacteria would we have, assuming exponential growth? Okay, so to get ourselves started here, we have to begin by putting in the initial number of bacteria. That was at the 2 hour mark, 256. And we have to put in the number of bacteria at the 5 hour mark, which is 541. Okay, so we put those two numbers in. The initial number of bacteria when we counted was 256. Now that didn't occur at the start. The first time we counted was at the 2 hour mark. So that's our initial count. A couple hours later, the count is 541. Now the part that can make this tricky is how many hours elapse between the 256 count and the 541 count. So you have to read it carefully enough so you can see this. Let me switch colors so I can highlight it a little bit. The 256 count occurred at the 2 hour mark, and the 541 count occurs at the 5 hour mark. So how many hours is it between the 2 hour count and the 5 hour count? The number of hours that would elapse is 3. Right? That's kind of a tricky number, a tricky value there. All right, so feel free to talk that over with somebody else in class to make sure we understand that. All right, now the idea is to solve for the rate. So let me put a little arrow in there. The only variable left in the equation is r, and that's going to be the rate of increase. I know that doesn't answer the question, but we first have to get to the rate of increase. So just like we solved the money problem on the previous example, here we have to solve for r. So we have to divide both sides by 256. So I'm just punching that out on my calculator. I get approximately 2.113. Yeah. And then I have to get the variable out of the exponent. So to get it out of the exponent, I have to do the inverse, which is take the log of both sides. What log? Because we have because we have base e on the right-hand side, we have to use the ln. So what I'm going to do is take the ln of both sides. All right? So on the right-hand side, ln and e are inverses of each other. So those two folks cancel each other out. And when I divide both sides by 3, r is then going to be equal to the ln of 2.113 divided by 3. Now that's clumsy to use, so I'm going to approximate that as a decimal. All right, so the ln of 2.113 divided by 3. If I punched okay, guys, I got about 2.249. So about 0.249, right? Now I know, again, that's not the question. What's the population of the bacteria 24 hours after we start? That's not the answer, but that's the rate of increase. This is the rate of increase for the bacteria. Now we can answer the question, which is, find the amount of bacteria when our first count was 256. The rate of increase is approximately 0.249, and the number of hours is pausing on purpose. All right, how many hours are elapsing here? It'd be real easy, of course, just to put in 24. But is it actually 24 hours? 24 hours from the start, yes. 24 hours from the start of the experiment, correct? Correct? But when did we make our first count? Remember, a sub 0, we're using 256. When did that count occur? That 256 count occurred at the 2-hour mark. So from the 2-hour mark to the 24-hour mark is a total of 22 hours. So the time that we have to allow to elapse then is 22. Real easy to put in 24, you just got to be careful of when the initial count was done. And then after that, it just becomes a calculator problem. We have to multiply 0.249 times 22, which is 5.478. We have to raise e to that power. So I'm just using my calculator to get there. We get 239.37, 239.37. And then we have to, these are all, I'm rounding, I should put approximately equal to on those son of a guns. And then multiply by 256, we'll round to the nearest bacteria. So we'll call it 61,278. So 22 hours after the first count, 24 hours in total. The number of bacteria in this culture then would be 61,278. Okay. Again, feel free to pause. Feel free to talk this problem over with someone else in class. All right? And I'll just continue to move on. Feel free to talk them over. Okay? The next one, giving you a different type of function to deal with. All right, it says here the number y of endangered animal species on a protected wildlife preserve from 1990 to 2004 can be modeled by this equation. And I'll highlight it here in something red or whatever here. So there's the equation. Please notice it's got a logarithm in it. Please notice it has a logarithm. Okay, and this equation is good for the values of t between 10 and 24. Okay, the question is, during which year did the number of endangered animal species reach 342? So maybe I'll flip my highlighter back on. Here's the question. When did the number of species reach 342? Okay, so what we're being asked to do is take our equation, which looks pretty complicated, but we're just being asked to replace y with 342. So if I do that for you guys, I replace y with 342, everything else just stays the same. Can you see the variable? Well, obviously there's just one left, it's right there. So can you guys help me solve for t? And the answer is sure, no sweat. Okay, what we can do is move the negative 117 to the other side by addition. Well, I suppose I don't need to show you that math, but oh well. So we add 117 to the other side. What do we get there, guys? 9, 5, and a 4. We get rid of times 159 by dividing. So we'll have the ln of t. And I think what I'll do here, guys, since this isn't going to turn out exactly, I'll use a decimal just to ballpark that son of a gun. So 459 divided by 159 is approximately 2.887. All right? Now, we don't want to know what the ln of t is. We just want plain old t. That's what we're shooting for. So how do we get there? Well, we have to somehow solve this log equation for t. And the key is the right-hand side has a log. The left-hand side does not. So when one side has a log and the other does not, we have to turn it back into an exponential. So a number raised to a power that's equal to something. Okay, so here we go. The log base, let me put an arrow in there so you know what I'm yapping about. The log base becomes the number base. Well, there is no log base, but because it's ln, that means the number base is going to be an e. What we're taking the log of becomes what the exponential is equal to, and a log is an exponent, so what a log is equal to, becomes the exponent. All right, so that's how we change from log to exponential. Now to get an approximation for the number of years, we could just raise e to that power. And I'm just using my calculator to get that approximately. So about 17.9 is the value for t. And in our case, the question was during which year did that occur? So let's see, 10 represented 1990, 10 represented 1990, so 17 would represent the year 1997. And then if we're 0.9 of the way through the year, what would that probably be? That'd be like probably November or December. Let's just for the heck of it call it November of 97. Okay. Again, feel free to pause. Get anything down you'd like into your notebook. Okay? All right. The next one. The State Game Commission released 100 animals into a game preserve. The agency believes that the carrying capacity of the preserve to be 1,200 animals, and that the growth of the herd can be modeled by this equation, where T is being measured in months. And just kind of keep that in mind. T isn't in years. T is being measured in months. How long will it take the herd to reach 1/2 of the capacity? Okay. Excuse me. So I'm going to do the solving first, and then we just need to talk about this. This is a different type of equation. Obviously, the previous problem was a log function. You're pretty familiar with those. The two before that, the bacteria and the money, were exponential growth problems. This one's a little bit different. It looks like an exponential because it has a variable in the exponent, but because it's in the denominator, it turns out a little bit different. So we'll talk about that after. First, let's just do the algebra stuff, the fun stuff. Okay? All right, so the question, let me choose a highlighter here. The question is, how long will it take the herd to reach 1/2 of the capacity? Up in the problem, it says the carrying capacity of the preserve is believed to be 1,200 animals. So half of the capacity, half of 1,200 then is going to be 600. So what we're wondering is, when is the population P become 600? So we leave the whole right-hand side alone, 1,200 divided by 1 plus 8 e to the negative 0.1588 t power. Just leave the whole right-hand side alone, and replace the left-hand side, P, population, with 600, half of the capacity. Okay? And then it's just a matter of solving that equation. Again, it looks exponential, and it will be. It just takes us a couple of steps to get there. So how would I solve this son of a gun with that variable in the denominator? Well, I would ask you guys to think of 600 as being a fraction by putting it on top of 1. And then I would ask you to cross multiply. So multiply diagonally this way, and multiply diagonally going this way. So the old algebra days, cross multiply. Let's do the tough one first. 600 times 1 plus 8e to the negative 0.1588t. So here we go. So 600 times 1 and 600 times 8 e to the negative 0.1588t power. There's the tough direction. So 600 times 1 is 600. 600 times 8 is 4,800 with the e attached. Cross multiplying the other way is easy McPeasy. 1 times 1,200 is 1,200. Now to solve, we'd have to move the 600 to the other side by subtraction. So 1,200 minus 600 is 600. We'd have to divide both sides by 4,800. So 600 divided by 4,800, gosh, I should know that. Is that 0.125? Let me double check that, guys. I'm just gonna make sure so I don't screw it up. Yep, so that's 0.125. And now it's just kind of a regular looking exponential equation. We have a variable in the exponent, and so we want to get rid of that base. All right, so how do we get rid of a base of e? Like we've done several times, we'll take the ln of both sides. All right, so I'll take the ln of the left-hand side and the ln of the right-hand side. Because the ln and the e are inverses of each other, boop, those two folks cancel each other out. So now the exponent drops down. And to get rid of the crazy decimal attached to t, we divide. So the ln of 0.125 divided by negative 0.1588 is going to get us the value for t. Of course, that doesn't make any sense to us, so we use our calculator to approximate this. Okay, so here we go. So the ln of 0.125 divided by negative 0.1588. Just going to double check I entered that okay. It looks all right. And so when I hit the old equal button, I get 13.1. And remember, t represented months. So that means it would take 13.1 months to get to half capacity. Half capacity. Okay? Alrighty. Now, I did want to do one other thing. That answers the question. We're done. But this original function with the exponential in the denominator, we just get an interesting looking curve to this. We get an interesting looking curve. So I'm just going to scooch off to the side and do two things with the camera here. Just haven't practiced this, so hopefully it'll turn out okay. Oops. Yep, so we can do this. So hopefully you can see this okay. What I have here is the equation that we were working with. 1200 divided by 1 plus 8 e to the negative 0.1588 power. Okay, no sweat. And then when I graph it, I set up the window. Oh, I should show you guys my window. So there's the equation again. Feel free to pause the video. All right, and I set up the window to look like this. I hope it's going to work out okay. I went x is 0 to 36. Remember, x is the number of months. And then the y values went from 0 to 1200. 0, no animals. 1200, which is supposed to be the carrying capacity, I think was the wording for the preserve. Okay, so there's the window. And now I'm going to hit the graph button. And I'm going to show you the graph, okay? So we hit the graph button, and I'm going to take that picture so I can pause it, and then you guys are just watching me do this, sorry. All right, so we end up with that as our graph. I'm going to shrink that down slightly. All right, just shrink that down. Okay, and what we find is we get a different type of curve, and it's called logistics. It's called a logistics curve. And so when we have the exponential sitting down in that denominator, the original equation that we have off to the side there is actually called a logistics function. And it has a really neat property. And the neat property is that it's a curve that has two horizontal asymptotes. It has two horizontal asymptotes, okay? Normally one asymptote is 0, and then there's another horizontal asymptote up higher somewhere, all right? Now in this particular case, in this game preserve problem, the upper asymptote would actually be located at 1200. So it represents 1200 animals. Now in theory, I know it doesn't make any sense, but if we drew the curve further back, in other words, we backed up time, you'd find that the curve would actually approach y equals 0. So it's a kind of a strange function. And the idea here, guys, is that in this game preserve, only so many animals can survive on the natural habitat. For the food supplies and water supplies and everything else, there's some sort of maximum number of animals that could survive. Okay? And I wanted to point this one out because this is actually the type of curve that everyone should have been talking about as the coronavirus and COVID have been spreading across your county, your state, your country, the world, whatever scope you want to look at. This is actually the type of function and the type of curve that the real scientists look at. The idea is that there's always going to be some sort of upper maximum number of people that can get the virus, right? It can't just go on forever. It can't, a lot of people think it's exponential and it'll just keep going up forever. It can't. It runs out of people. So it's actually a logistics curve. So what would happen if nobody had taken any precautions, if nobody had done anything, we just let it go, what would have happened is it would have gone up like crazy for a long time, but then eventually, let's just say in our country, it would start to run out of new people to infect, and so the number of people getting COVID would slowly start to slow down, right? Eventually, in theory, it probably wouldn't happen, but in theory, this would then approach the upper limit, would be the total population of the United States. So at some point, it would level out somewhere close to 330 million people. And of course, you could do the same thing just for our town, for our school for that matter, for our school, our town, our county, our state, our country, the world. You could create a logistics curve for any disease like COVID or anything else that ever comes up. So I just wanted to point that one out to everybody. All right, kind of an interesting curve, and it's something you never hear about. If you really get into the background of the scientists working on COVID and the coronavirus, you'll actually find equations. Let me back up to it. You'll find equations. They're a bit more complicated than this, but it's the same idea. It's the basic idea. Where you'd see, let me choose a different color here. You'd see this exponential in the denominator. You'd see this exponential downstairs. Okay? All right. And I just have one more. I made this too big now, so I got to shrink that up. So I've got one more application problem. And this one's going to be essentially just totally on your calculator. This one's going to be totally on your calculator. It says the test scores, let me choose a color here. The test scores at the Dramy Institute of Technology can be modeled by the following normal distribution. And before I give you the equation, obviously you guys can read it, where X represents the test scores, and then it asks you to sketch the graph and estimate the average test score. Okay, so the idea here, guys, is to remember, where's the phrase here? Normal distribution. All right, I know it's been a couple of years, but we've actually talked about normal distributions in the past. Back in algebra days, we talked about normal distributions. And what that referenced was the way statistics, data values, are spread out for naturally occurring situations. And when naturally occurring situations get graphed in terms of frequency, you'll always end up with this shape. Some people like calling it a bell curve, but technically it's called a normal distribution, right? And like we did in algebra days, we could apply this to the average height, or not average height, the heights, I should say, the heights of women in the United States, or the heights of men in the United States, or the weights of adult men in the United States, or the average field-dressed weight of a deer in the state of Minnesota. They always look like this. And just, you don't have to remember this. You don't have to take notes on any of this. But the idea is the average value always occurs somewhere in the middle. And then we have these things that we learned about in algebra called standard deviations. Right? If you don't remember the notation, it's no big deal. Don't worry about it. But they were called standard deviations. And what we learned about was that when you're within one standard deviation of the average, 34% on either side of the data values will be within one standard deviation. Or if you put those together, 34 and 34 is 68. So 68% of all data values occur within one standard deviation of the average, or the mean. And then if you go out another standard deviation, so you go out another one to the right, or You go out another one to the left, then you get another 13.5% of all the data values. All right, so we did things like IQ problems. The average IQ of someone in the world is 100, and the standard deviation is 15. So if I go up a standard deviation, I'd be at 115, and if I go down a standard deviation, I'd be at 85. So what that would tell us is that 68% of the people in the world have a IQ between 85 and 115. If you go another standard deviation, another 15 up, another 15 down, now when you put all of those folks together, what is that, guys? That's 68, 78, 88. I think that's 95. If am I doing that math right in my head? I better double check that. Sorry, guys. 34, 13.5, and 13.5. What is that? Yeah, 95. If you go out another standard deviation, see, this was 68%. If you go out another standard deviation, that means 95% of the people in the world would have an IQ between 70 and 130. Okay, so that's what we used to do in Algebra 2. You do a lot more of this if anyone takes college level statistics. You'll do a lot of this. Okay, but back to our problem. Okay, when we look at this curve, all right, that shows the test scores at the Doremi Institute of Technology, and they can follow this model. How can you sketch this graph and estimate the average test score? Okay, again, it's going to be nothing but a calculator problem here. And so what I'm going to ask you guys to do is punch this in your calculator. And I didn't do this beforehand, so it's going to take me a minute, sorry. So 0.0798, yep, times E. And then E is going to be raised to kind of a crazy power. It's going to be raised to the negative parentheses, x minus 82 squared divided by 50. And I just got to double check I've typed it in okay. 0.0798 times E raised to the negative x minus 82 squared divided by 50. Yep, looks okay. And I'll turn my camera on. I'll turn my camera on so you can once again see the equation on my window, calculator window. Right, so there's that. Right? But then I want to graph this. I want to graph this function. And since my window is still set from the game preserve animal problem from before, I'm going to have to adjust my window. Okay? Now, if you adjust it to kind of a normal looking screen, you know, even if you went something like -6 to 6, and -4 to 4. You know, you go back to kind of a normal window and you hit the old graph button, you just see nothing happens. You're like, well, what in the world? How am I supposed to know? So the main trick to this problem is to adjust the settings. All right, adjust the settings on the window. Okay, so what I need to do is I need to adjust the window, and I'm not exactly sure, I didn't practice this one, but I'm going to try the x's between, I'm just going to give it a try. I'm going to go between 60 and 100. Okay? Now remember, the x's were the test scores on some exam. So we're going to look at exams between 60 and 100. We'll adjust that if we need to. Then the y's are the frequency. And here's the trick. We've got to make the y max really small. We've got to make the y max really small. And I'm going to try 0.1. I honestly don't remember off the top of my head if that's going to be good or lousy, but I'm going to try 0.1 and hit the old graph button. Okay? Oh, and I didn't do too bad. So now let's see, I'm going to take a picture of that because it did turn out to be a pretty nice shot, and it'll just take me a second to get through this. And obviously I'll shrink that down because it's just oversized. There we go. And so you can see, even though the question should be, wow, how would I ever know to get a window like that? You're absolutely correct. It would be tough, right? But there's the graph. And then the second part is, what's the average test score? So the average, if you might remember from algebra class, is always going to be at the high point of the curve, the bell curve, the high point of the bell curve, right? And so what you can do is tell your calculator to do a calc, and then under calc, choose max. Remember, this is the one where you pick a point on the left side of the hilltop, pick a point on the right side of the hilltop, and skip the guess. Skip the guess. And what you'll find, what it'll tell you is that x is going to be equal to 82. And so the average test score on this exam, would then be 82. And once you've seen it, once you've seen that result, you think, well, I can see where that's coming from. It's coming from that parentheses. Obviously correct. Okay? But just a little bit of fun there, just a little bit of fun. A little bit of a review about normal distribution curves from algebra days. Okay? So that's all I'm going to do on this video. Obviously, I'll be back on Monday so we can take care of more problems and more questions and so on when I get back. So use whatever time is left to work on the assignment. Put your hoods down. No more hoods. And then we'll see. Have a good weekend, and then we'll see everyone on Monday. See you later.